Hi, my name is Elad Natanely, and here we have my microprocessor for the final project for Digital Systems Fundamentals. As you can see, my microprocessor consists of a lot of labeled chips. So here we have the FSM, the output decoder, the register for A, the ALU, register for B, register for the input, and the register for the output connected to an LED so you can see what the bus is outputting to the ROM, from the ROM and the program counter in unison. I'm going to walk you through some of the chips that I used and some of the individual components that make up each of the chips. So to begin, we have an SR latch. You see that when both of them are high, we have no output. But when one is high, we'll see that we have the output of the opposite NOR gate. So when R is going to be high, we'll see that we have Q bar high. And when both are high, we see that we have neither Q nor Q bar high. And I made a D latch using the SR latch. And we see that when C is high, we have no change. And we see that D is going to be the one leading the change, but only when C is high. And then we can obviously clear this, and it'll set us back to our initial state. And we have a negative D latch, which is going to work in the inverted fashion compared to the positive D latch. You see that when C is high, nothing happens. When D is high, it's going to control the change of the output, because the other one worked when C was high, and it's going to work when C is low. And using this D latch, we can make a flip-flop. This is going to be a rising edge flip-flop. So when D is high, nothing happens until the clock is also going to be high. We see that when we change D, nothing happens. When the clock goes low, nothing happens. But when D is low and the clock goes high again, we see that we have Q bar high. And a big part of microprocessor is having data being read when desired. And in order to have this occur when we want, we have to include a load or an enable bit. So we can clear it and start from the beginning, and we can see that if we expect the same output to happen when we have a normal flip-flop, we see that on a rising edge, we see that there's no change. And the only time a change will occur is when load is high. And this makes it act as if it was a normal flip-flop. So we see that now Q will be high and Q bar will be low when the clock is high. And when we make D low, we see that when the clock is going to be high once more, Q bar will be high. And then out of this, we can make a 4-bit register that takes 4-bit inputs and works exactly like a 1-bit register, except 4 bits. And this is also work when load is high. So we can clear this, and we can see that the only way to get these inputs and outputs to match is to have both load high and the clock high as well. And a change will only be mimicked when the clock is high once more. And then we can make an FSM using these flip-flops. It's a fairly simple flip-flop. It takes into consideration the next states and the current states. So we have 2 fetch and 2 execute states that are being cycled through with the rising edge of the clock. So we'll see that if we want S1 to be reflected, then we have S1 high on the rising edge. If we want S0 to be reflected, we need a rising edge. If we want both to be reflected, we have to have both lit up. And if we want none to be reflected, we want it just like that. And then we have the output decoder. So using the 2 state bits from S1 and S0 and the 4 instruction bits, we get our 9 desired output bits that are going to be really running the show here. In terms of the microprocessor, we have our 9 output bits here. So this does is really going to create the signals that are going to control these 9 output bits. It's also going to be able to enable the tri-state buffers that are connected to the register and the ALU and the instructions, as we see here. In terms of ENO, ENA, enable O, enable A, enable B, we see that we have those here. Those are going to be able to, we're going to use tunnels so that way they go to the load. And the input from the registers is going to enable the registers right from the bus. And in terms of EA, EALU, E instructions, and EIR, these are going to be able to enable the registers to output to the bus rather than before they're going to be able to, rather than for the ENA, ENB, and O, which are going to be able to see information and take it in from the bus. And so here we have the connected FSM with the output. And over here with our XOR gate, we're going to have our next state logic that's just going to be able to cycle through the 2 fetch and 2 execute states. And after that, we can make a 1-bit adder, which is really going to be our basis for our program counter. It's the most essential building block, I guess, for it. So here we just have a regular adder. If we have A, then we know the sum is just going to be a 1. If we have 2 inputs, we're going to have a 0, or we're going to have a low and a carry. And if we had 3 inputs on high, we're going to have both a carry and a sum value. And then one level of abstraction further, we can make a 4-bit adder, which essentially just does the same thing, but just does it in 4 bits. We're not going to have any carry yet because no bits are overlapping. But when we do get a carry, it's going to be reflected there. So it's just essentially a 1-bit adder. They serve the same purpose. Just one is in one bit and the other is in 4 bits. And then from there, we can make our counters, which are then going to be used to make our arithmetic logic unit, which is essentially going to be a 4-bit counter, which we have reflected here. So when we make our 1-bit counter using our flip-flop and a 1-bit adder, hold on, we see that when we want to go, oh, so this is also enabled. So when the only way this would work is on the high load or high enable. So we can clear it in order to see its effects. So we clear it, and we have load high, and we have the rising edge of the clock. We see that this isn't properly working because I didn't open it properly. For some reason it's not. Alright, okay, so we'll come back to this one. But in our 4-bit counter, which is basically our 1-bit counter, so this isn't working. I'm sure this is probably a bug with Logisim, but our 4-bit counter will properly work. So when we cascade these flip-flops on our 1-bit adders to create this, the 1-bit counter isn't entirely necessary, but once we make our 4-bit counter, we're going to want it to count upwards because we're going to be, when we do make our arithmetic logic unit, we're going to be cycling through our instructions, and they're going to be 16 of them, and we're only going to be wanting to go up. We can make it go down, but for the sake of this, it's going to go up. So when we have clock on high, and we're going to want to increment it, it's going to increment upwards in binary with the clock on high and increment on high as well. So it's just going to go from 1 to 2, so we can clear it. And we can see that it goes from 1, and clear is still on high. So it's going to go from 1 to 2 to 3 to 4 to 5 to 6 to 7 to 8 until it gets to 16, because there's going to be 16, until it gets to 15, because there's going to be 16 instructions to cycle through once we do have our ROM. So here we have our arithmetic logic unit, which exactly consists of a 4-bit 4-bit adder, 4-bit counter rather. But what actually this is, no, it's actually going to be the 4-bit adder because we want this to be able to both add and subtract 4-bit binary numbers. In order to take care of this, we're going to have a multiplexer here that's going to be selected by the adder subtract pin, well, the inverted adder subtract pin. So on low, we're going to see that there's going to be subtraction, and one there's going to be an add. And the reason for this multiplexer is because we want this to perform a 2's complement on a value of b. So that way when we invert it, we're going to have an entirely inverted number, and that's essentially going to negate it, and then we're going to add 1 to it using the Cn of the 4-bit adder. So inverting and adding 1 is essentially the same as subtracting in 2's complement. So when we do want to subtract, so when we have this pin on low, we're going to see that this is on high. So the inverted value of b is going to be selected, and then Cn is going to be 1 adding to b, inverted value of b. So we see that when we want to subtract 1 and 1, we're going to have a 0. And when we want to add a 1 and 1, we're going to have this on high, and we're going to have 2 here in our output. And once we have all of these taken care of, we can look at the main circuit itself of the microprocessor. So two things I did not cover in my individual components are going to be these two AND gates that have their inputs negated. So this is going to, this one right here, this AND gate, is going to enable the instructions to be read from memory. This connection from here to here. And this one with the leftmost bit negated is going to be able to increment the program counter. And it's going to allow new instructions to be handled. And this is connected to our counter, our program counter. So what this in effect is going to do is going to allow, so once we have our program counter connected to our ROM, we're going to be able to cycle through these instructions that are going to be fed. And these instructions, instructions in the data that are going to be fed from the bus and through. And the event is going to be reflected in this output LED I have here is connected to the output register. So once we do clear everything and we have our circuit ready to go, I have some preset instructions in the ROM. So I have a 5.2 here. So once the 5.2 is ran, that means 2 is going to be loaded into the LED. And this 40 is going to, once the 40 is ran, a 40 is going to allow the 2 to appear on the LED. So let's see that that's reflected. So we have the 2, and now this 17 instruction that we have right here is going to reflect, so the 1 in front of it is going to reflect an addition, so that's from the ALU. It's going to reflect an addition of the integer 7. So we should see a 9 reflected in the LED once this is run. Well, actually the 9 will be reflected once the 40 is run again, because the only reason that these things will appear on the LED is because of that 40 there. So we see that we have the 9. And next we will have a 2.5, and that 2.5 represents a subtraction because of the 2 in front of it, and a subtraction of the integer 5. Once you run that, we should see a 4. So we do see the 4. And next we'll have a 30, and the 30 means that we will feed in an input value from the input register. So if we'd like to pick, let's say, 2 for, no, this will be, okay, we have 3 for instance, so 0011 from the register input. Once we do run the clock on that, we see that we'll have a 3 after the 40 is run, so we have a 3 there. And next we have an addition of 3, 1, 3, so we should have 6 reflected there. And then we have another addition of 5, so we should see an 8 reflected there. Well, actually, we're in hexadecimal, so we should see an 11. So the hexadecimal equivalent of 11 will appear once the 5 is added, and we have a lowercase b. And here we have another addition, and we have a subtraction of 5 now. So subtraction of 5 from the hexadecimal value of b. And we have another 6. So basically we just undid the addition of 5, so we're back to 6. And now we have finally an addition of 2, so we should see 8 as our final output once all the instructions are ran. And we can also change our inputs. We can have just entirely the addition of 12 throughout for our microprocessor. We just have the addition of 2 rather. So we can have ticks enabled and we can simulate this at 16 Hertz, and we'll see that we're just adding 2 constantly. 2, 4, 6, 8, and then from there the binary equivalents of all these values are going to be reflected. So this is my microprocessor that handles positive numbers and increments upwards, but these can be changed and we can make it more complex, but for now this is the working product for my microprocessor. Thank you.